13.8 billion years ago, everything that exists sprang into being in an event known as the Big Bang. Every atom in every body, every star that has ever burned, every thought that has ever crossed a human mind, traces its lineage back to that single instant. It is one of the great triumphs of modern science, confirmed by mountains of evidence, etched permanently into the light of the cosmos itself. And yet the moment this fact is accepted, a far more dangerous question rises up right behind it, like a shadow that was waiting for the sun to appear so it could finally be cast. If the universe began, then something must have preceded that beginning. There must have been a moment, 1 second earlier, in which the conditions for such a beginning were already set in place. This sounds like the simplest question a curious mind could raise. It is, in fact, one of the most violent questions that can be thrown at the laws of physics, because it doesn't just strain our equations, it breaks the very grammar used to think about reality at all. This is territory where cause and effect, before and after, here and there, start to lose their meaning entirely. And before that territory can even be entered, a beautiful, comforting, deeply intuitive image that most people carry around without ever realizing it has to be burned down first. Picture an enormous dark room. Silent, empty, cold. And then, somewhere in the middle of that infinite black room, a spark ignites, and an explosion of light and matter goes roaring outward in every direction, filling the emptiness that was patiently waiting there before it. That image feels right. It feels almost cinematic. It is also, according to everything modern cosmology understands, completely wrong. There was no room. There was no empty stage waiting for the actors to arrive. There was no outside from which to watch the show begin. And by the time this idea has been traced all the way to its logical end, it becomes clear why some of the greatest minds in the history of science have concluded that the question of what happened before the Big Bang may be less like asking what happened before a fire started, and more like asking what lies north of the North Pole. Not mysterious, not unknown, simply, structurally, without an answer, because the very language of before dissolves the moment it is applied there. But that is not the end of the story. It is only the first wall standing in the way, before the real exploration can begin. Because beyond that wall, physics has not gone silent. It has offered 4 extraordinary, rigorously reasoned possibilities, each one stranger and more magnificent than the last, for what might lie on the other side of existence itself. A previous universe, dying in a catastrophic collapse, only to rebound into a new one. An infinite ocean of energy, boiling eternally, spawning universes like bubbles in a pot of water brought to a furious boil. A cosmic collision between invisible membranes of reality, vast structures floating in a hidden dimension beyond ordinary perception. And, threaded through all of it, the humbling reminder that this entire inquiry proceeds like a team of detectives arriving at the scene of a fire millions of years after the flames went out, forced to reconstruct the blaze from nothing but the pattern of the ash. Every human culture that has ever existed has told itself a story about the beginning. A god speaking light into darkness. A cosmic egg cracking open. A serpent coiled around the void, waiting. These stories were never really about astronomy. They were about a deeper, more urgent need. The need to believe that nothing does not simply sit there, uncaused, forever. Something, humanity has always insisted, must have started it. And so when modern cosmology declares, with all the authority of mathematics and measurement, that the question of before may not even be a coherent question at all, it doesn't just challenge a scientific model. It challenges something much older, something buried deep in the architecture of how human beings have always tried to make peace with existing. That wall is where this story begins, and it is worth examining exactly why it stops us before uncovering what waits on the other side. Space and time, in the world of Isaac Newton, were simple things. Space was an empty stage, fixed and unmoving, upon which the events of the universe played out. Time was a clock ticking steadily in the background, indifferent to everything happening within it, the same everywhere, for everyone, always. It was a comforting picture. It was also, we now picture apart in the early 20th century, and replaced it with something far stranger and far more beautiful. Space and time, he showed us, are not a stage and a clock. They are a single, unified fabric, something physicists now call space-time, and this fabric is not indifferent to the universe at all. It is woven directly into the matter and energy that exists within it. Mass bends this fabric. Energy warps it. A star curves the space around it the way a bowling ball curves a stretched rubber sheet, and that curvature is what we experience as gravity. Time itself flows at different rates depending on how deeply you sit within that curvature, slower near a massive object, faster far away from one. Space and time are not the container for physics. They are participants in it. This single idea, once you take it seriously, changes everything about how we have to think about the beginning of the universe. Because if space-time is woven from matter and energy, then space-time cannot exist independently of matter and energy. There is no empty fabric sitting there, waiting patiently for something to happen to it. The fabric and the event are the same thing. Now follow this thread all the way back. As we run the expansion of the universe backward in time, like rewinding a film, everything we see moves closer together. Galaxies rush back toward each other. The vast distances between clusters of stars begin to shrink. Rewind further, and matter itself becomes compressed into smaller and smaller volumes, growing hotter and denser at every step, atoms crushed apart into their constituent particles. Those particles crushed into a state so extreme that our best theories of physics begin to strain and crack under the pressure. Keep rewinding, and you approach a point where the entire observable universe, everything within our cosmic horizon, is compressed into a region smaller than an atom. Keep rewinding still, and you arrive at what physicists call a singularity, a point, or perhaps better described as a state, of infinite density, infinite curvature, where the equations of general relativity simply stop producing meaningful answers. They don't predict something strange. They predict nothing at all. They break. It helps, at this point, to sit with just how strange this rewinding process really is, because it is easy to let the words slide past without absorbing their weight. We are not simply saying that matter used to be more crowded together, the way a city feels more crowded during rush hour. We are saying that the actual distances between every point in space were smaller, that space itself, the very medium in which distance is measured, had less of itself to go around. A galaxy a billion light years away from us today was not, a long time ago, simply closer. The billion light years of space between us and it had not yet come into being. Space was not waiting there, empty, for the galaxy to travel across it. The space and the galaxy grew together, hand in hand, out of a shared origin. This is the singularity at the heart of the classical Big Bang model, and it is often misunderstood, so let's be precise about what it actually means. It does not mean there was a tiny dot of matter floating in empty space, and that dot exploded outward. There was no space for it to float in. The singularity was not an object sitting inside spacetime. It was the total absence of a defined spacetime at all. Space had not yet acquired a size. Time had not yet acquired a direction. Neither the where nor the when had been established, because both are properties that emerge from spacetime, and spacetime itself had not yet come into structured existence. This is the point where the question, what happened before, runs headfirst into the wall. Because before is a statement about time. It presupposes a timeline along which one moment precedes another. But if time itself, as a coherent, flowing dimension, only comes into existence at that singularity, then asking what happened before it is not like asking about an unexplored country beyond a border. It is like asking what note came before the very first vibration of a string that had never yet been plucked. There is no prior moment to point to, because the concept of a prior moment is itself something that had to be built, and it was only one of the sharpest minds ever to wrestle with this problem, offered an analogy that has become one of the most elegant in all of science communication. Picture a traveler standing exactly on the north pole of the Earth, asking which direction leads further north. The question feels grammatically valid. It has the right shape, the right structure, subject and verb and object, all in their proper places. But it is a meaningless question, not because the answer is hidden or difficult to find, but because the very concept of north ceases to apply at that specific point. North is a direction defined relative to a location on a sphere, and at the pole itself, every direction one could possibly walk is south. The concept simply doesn't extend past that point. There is no mysterious, undiscovered region further north waiting to be explored. The question itself dissolves the moment it is asked at that exact location. Time, near the Big Bang, may behave the same way. As you approach the singularity, some versions of quantum cosmology suggest that the dimension we experience as time gradually rotates, mathematically, into behaving like another dimension of space. The distinction between past and future, between before and after, smooths out and disappears, the way the distinction between north, south, east, and west smooths out and disappears as you approach the pole of a globe. There was no frozen, silent moment sitting there, waiting through some kind of external, prior time for the universe to finally get around to beginning. The very notion of waiting requires time to already be running. And time was one of the things being created. Consider how strange the North Pole analogy actually is, once you let it sink all the way in. Nobody standing at the pole feels cheated by the question having no answer. Nobody insists that there must be some hidden, undiscovered direction, further north than north, simply waiting for a clever enough explorer to find it. We accept, without much struggle, that the geometry of a sphere simply runs out at that point, and that our ordinary compass directions are a local convenience, not a universal law binding all of space. And yet, when the same logic is applied to time, something in us resists far more fiercely. We are willing to accept the limits of geography. We are far less willing to accept the limits of causality, because causality feels less like a convenient local description and more like a law we imagine the entire universe must be obligated to obey, everywhere, always, without exception. This is a genuinely difficult thing for the human mind to absorb, because our brains evolved to survive on the plains of Earth, tracking the passage of seasons, the movement of prey, the setting of the sun. We are creatures built by evolution to assume that every event has a before. Every cause has a preceding cause. It is, quite literally, one of the deepest instincts we carry, wired into us by 100,000 generations of ancestors for whom that assumption was true and useful, because on the plains of Earth, it always was. A predator's snarl was always preceded by its approach. A storm was always preceded by darkening clouds. The mind that survived best was the mind that most reliably assumed a before existed for every after, and went looking for it. But the universe does not owe our evolutionary instincts an explanation that fits comfortably inside them. Reality, at its most fundamental level, is allowed to be stranger than the intuitions of a species of primate that learned to throw spears at woolly animals on an ordinary, temperate afternoon. So we hit the wall. Classical general relativity, the same theory that so beautifully describes orbiting planets and merging black holes and the graceful bending of starlight around the sun, simply cannot tell us anything about what, if anything, existed prior to the singularity, because the theory itself ceases to function at that point. It is not a lack of imagination on the part of physicists. It is a hard mathematical boundary. Asking general relativity what came before the singularity is like asking a map of France to describe the geography of Japan. It is not the map's job. It was never becomes genuinely exciting, rather than simply humbling. Because the singularity predicted by classical general relativity has long been suspected, by many of the physicists who take it most seriously, to be not a true description of reality, but a symptom of a theory being pushed far beyond the domain where it was ever meant to apply. A singularity of infinite density is, in a very real sense, a mathematical scream, a signal that the equations have run out of road, rather than a genuine physical statement about what nature actually does at extreme densities. And when physicists in the 20th and 21st centuries began asking what theory might replace general relativity at those extremes, the answer they kept arriving at, again and again, was quantum mechanics. The physics of the impossibly small. And when you bring quantum mechanics to the doorstep of the Big Bang, the wall doesn't just block the path forward. It begins to reveal a door. It is worth remembering, too, that the wall we hit at the end of part 1 was never really a wall built by nature. It was a wall built by the limitations of a single theory, general relativity, being asked a question it was never equipped to answer. A theory describing smooth, continuous curvature simply has no vocabulary for what happens when that curvature is compressed past all reasonable limits. It is a little like asking a beautifully accurate map of ocean currents to describe what happens to a single water molecule as it evaporates. The map was built at the wrong scale for that question. It doesn't mean the answer doesn't exist. It means we need a different kind of map. For most of the history of physics, gravity and the quantum world lived in separate kingdoms, refusing to speak to one another. General relativity ruled the large, the massive, the cosmic. Quantum mechanics ruled the small, the subatomic, the strange. Each worked with astonishing precision in its own domain, and each, when you tried to apply it to the other's territory, produced nonsense. But there is one place in all of existence where both kingdoms are forced to meet, where something is simultaneously incomprehensibly dense and incomprehensibly small, the birth of the universe itself. And it is here, in this one narrow doorway, that physicists suspect quantum gravity, the still unfinished theory that would unify these two kingdoms, must finally have its say. One of the most compelling ideas to emerge from this frontier is a proposal that reframes the entire question. It suggests that the Big Bang was not a true beginning at all, but a bounce. The reasoning starts with a simple but profound suspicion held by many researchers working on quantum gravity, that space itself is not infinitely divisible. Just as matter, when you look closely enough, resolves into discrete atoms rather than a smooth, continuous substance, some theories of quantum gravity suggest that space and time themselves may be built from tiny, indivisible units, sometimes described as quantum grains of geometry, at a scale almost inconceivably small, roughly 100 billion times smaller than a proton. This is called the Planck scale, and it may represent an absolute floor beneath which the concept of a smooth, continuous space simply stops applying, the same way a photograph, however sharp, eventually dissolves into individual pixels if you zoom in far enough. If this is true, it changes the entire story of collapse. In the picture painted by classical general relativity, matter can be crushed down into an infinitely small point, because the equations treat space as endlessly divisible, with no smallest unit, no final grain. But if space has a true, fundamental granularity, then there is a limit to how densely matter can be packed. At some critical point, the fabric of space simply cannot compress any further, the way you cannot squeeze a bag of marbles down to a volume smaller than the marbles themselves, no matter how hard you press. The pressure has to go somewhere. Think of it this way. Imagine trying to pour an ever-growing volume of water into a container, believing the container can shrink without any limit at all. Classical physics tells the story as though the container truly has no floor, no smallest possible size, so the water, meaning matter, and energy, can be compressed forever, approaching an infinite density that is never actually reached but is always, mathematically, the destination the equations are racing toward. Quantum gravity suggests something very different, that the container has a floor after all, a final, non-negotiable smaller size, and that once the water reaches that floor, it has nowhere left to go but back up. The pressure that theory always assumed would keep building forever instead finds a wall of its own, big bounce hypothesis, one of the most captivating ideas in modern cosmology. In this picture, our universe was not born from nothing. It was born from the death of something else, a previous universe, or a previous phase of existence that had spent an unimaginable span of time expanding, cooling, forming its own stars, and living out its own history before gravity, that patient, relentless, universal attraction, finally won. Slowly, and then with terrifying speed, that prior universe began to contract. Its galaxies, over eons, drew closer together. Its stars burned out and grew cold. Space itself began to shrink, matter and energy crushed into ever smaller volumes, temperatures climbing to levels that would make the heart of a star look gentle by comparison. And then, as that collapsing universe approached the fundamental granularity of space itself, something extraordinary is proposed to happen. Instead of collapsing all the way to a true, infinitely dense singularity, the immense pressure of quantum gravity is thought to act like an unimaginably powerful spring, coiled tighter and tighter as the universe shrank, until it could coil no further. And at that critical threshold, the collapse reverses. Not gradually, not gently. In an instant, on a timescale far shorter than anything we can intuitively grasp, the contraction becomes an expansion. The dying universe's final, catastrophic compression becomes the newborn universe's first, explosive breath. This is the bounce. And what we call the Big Bang, in this framework, is not the beginning of everything. It is the rebound. There is something almost unbearably poetic about this idea, and it's worth sitting with it for a moment. It suggests that existence itself may not be a single, one-time event that sprang from nothing, but rather a heartbeat, an endless, rhythmic cycle of expansion and collapse, death and rebirth, playing out again and again across a span of time so vast that our own universe's entire history, all 13.8 billion years of it, all of human civilization, every star that has ever burned, might be nothing more than a single beat in a cosmic pulse that has been repeating since before repetition itself had meaning. Crucially, this is not simply a beautiful story. It has genuine mathematical teeth. Approaches such as loop quantum cosmology, a serious research program within quantum gravity, produce equations in which the classical singularity is replaced precisely by this kind of bounce, a moment of maximum density followed by re-expansion, without ever passing through the infinite, meaningless breakdown that plagues the classical model. In these models, the before that our forbidden question was searching for does, in a sense, exist. It is a real, physically describable phase, the final contraction of the universe that came before ours. And yet, tantalizingly, most versions of this theory suggest that the bounce itself may scramble almost all detailed information about that prior universe, smoothing away the fine structure of what came before in the extreme violence of the transition, in the same way a wave crashing on a beach erases the intricate sandcastle that stood there moments earlier, leaving only the faint, generic outline of the fact that something existed and was crushed into ours. So even in the most hopeful version of this framework, an honest, satisfying account of the previous universe's history, its stars, its worlds, whatever may or may not have lived upon them, is likely to remain forever out of reach. We may be able to say, with growing mathematical confidence, that something came before. We may struggle enormously to ever say precisely what. There is a particular kind of humility built into this framework that is worth pausing on. It does not promise us a window into the previous universe's civilizations, if any existed, or its constellations, or its particular arrangement of galaxies. It promises us something narrower and, in its own way, more honest, a mathematically consistent account of how a universe could avoid the impossible infinity of a true singularity, replacing an unanswerable question with a physically describable process, even if the fine details of that process remain forever smoothed away, like a signature erased by the very ink that once wrote it. This is only the first of the doors quantum cosmology has opened. Because if a single universe can bounce, breathe out and breathe back in, the natural next step pulls the scale of the discussion far beyond anything a single cosmic heartbeat could contain. The question of what exactly we have to leave behind the comfortable idea of a single universe, expanding, contracting, and bouncing in isolation, and step into a framework that asks us to imagine something almost too vast for the human mind to hold on to. Picture, if you can, not a universe, but a boundless, formless field of pure energy, without edges, without a center, without a beginning or an end, existing outside of anything we would recognize as ordinary space or ordinary time. Physicists call this hypothetical substrate the inflaton field, or more broadly, eternal inflation, and the picture it paints is less like a single explosion and more like a vast, roiling, endlessly boiling ocean of potential. This idea grows out of a theory called cosmic inflation, first proposed to solve a series of puzzling features of our own universe that the simple Big Bang model, on its own, struggled to explain. The cosmos, on the larger scales, is remarkably uniform in temperature, even across regions so far apart that light itself would never have had time to travel between them and even things out. The geometry of space, as best as it can be measured, sits astonishingly close to perfectly flat, even though countless other geometries were mathematically just as possible. Inflation answers both puzzles by proposing that, in the first unimaginably brief fraction of a second after the Big Bang, the universe underwent a period of expansion so extreme, so violent, that a region smaller than a single proton was stretched, in less time than it takes light to cross an atom, to a size larger than the observable universe we see today. Space itself expanded faster than light, which sounds like it violates relativity, but does not, because it is space itself doing the stretching, not any object moving through space. Nothing was breaking the speed limit. The racetrack itself was simply growing. To appreciate how strange this is, imagine two regions of the sky, on precisely opposite sides of us, so far apart that even light, traveling at its absolute maximum speed since the Big Bang, would not have had enough time to cross from one to the other. And yet, when we measure the temperature of both regions with extraordinary precision, they match, almost to within 1 part in 100,000. Two places that should never have had the chance to compare notes, to exchange so much as a single photon, are nevertheless nearly identical twins. Inflation resolves this by proposing that these two regions were once close enough to interact freely, to reach the same temperature the way soup evens out in a pot, before being flung to opposite sides of the observable universe by that single, violent burst of hyperexpansion. What looks impossible only looks that way because we forgot how small everything used to be. This theory of inflation, extraordinarily well supported by precise measurements of the ancient light left over from the early universe, carries within it a further, almost dizzying implication, one that many of its original architects, including physicist Andre Linde, came to believe was very difficult to avoid. If the field driving this inflationary expansion behaves according to the equations of quantum mechanics, then it is subject to quantum fluctuations, tiny, random, unpredictable jitters in its energy, the same fundamental uncertainty that governs the behavior of every particle in existence. And in most regions of this vast inflating field, these fluctuations mean that inflation does not stop uniformly, all at once, everywhere. Instead, inflation continues to drive most of the field to expand forever, eternally, while only in certain isolated pockets, regions where a quantum fluctuation happens to push the local energy down into a lower, more stable state, does inflation grind to a halt. When inflation stops in one of these pockets, all of that immense stored energy has to go somewhere, and where it goes is into the creation of particles, radiation, and matter, a violent, localized transformation known as reheating. This local pocket, cooling and filling with matter, becomes what we would recognize as a Big Bang, an explosive birth of a universe with its own space, its own time, its own laws taking shape as the energy settles. But crucially, this is only one bubble, because the eternal inflationary field around it never stopped expanding. It continues to boil, endlessly, forever, And every so often, in some other region of this boundless ocean, another quantum fluctuation triggers another local collapse into another bubble, another Big Bang, another universe, spawned independently, unaware of, unreachable from, and utterly the multiverse. And it is critical to understand that it did not arise from science fiction or idle speculation. It emerged as what many physicists consider a nearly unavoidable mathematical consequence of taking the extremely well-tested theory of inflation and following its own internal logic to its natural conclusion. If inflation happened at all, and the evidence strongly suggests it did, then eternal inflation, and the endless production of separate bubble universes, appears to be an exceptionally difficult conclusion to avoid, however uncomfortable it may be. Under this model, our Big Bang was not the beginning of existence. It was a local event, the moment our particular bubble, our particular pocket of settled, cooled, structured spacetime, condensed out of the boiling, eternal field around it. Beyond the edges of our universe, if the word beyond can even meaningfully apply here, that field is still inflating, and has been inflating, and may go on inflating, forever. Somewhere within that endless expanse, by some estimates, an incountable number of other bubbles, other universes, may exist, each with its own Big Bang, each expanding outward from its own singular, local birth. Some, according to certain versions of the theory, might have wildly different physical constants, different numbers of dimensions, entirely different rules governing matter and energy, shaped by which particular quantum fluctuation happened to trigger their formation. Others might be nearly identical twins of our own. There is a peculiar kind of vertigo that comes with taking this seriously. If eternal inflation is correct, then our Big Bang was not a singular miracle, unrepeatable, unique in the history of existence. It was closer to an ordinary event, the kind of thing that happens constantly, endlessly, throughout a field that has been boiling for longer than any timeline within our own universe could ever measure, because that field's clock, if it even makes sense to speak of one, was never synchronized with ours to begin with. We tend to think of our universe's birth as the most extraordinary event imaginable. Eternal inflation asks us to consider the opposite possibility, that it may be one of the most common events imaginable, repeated on a scale so large that common barely captures it, the way a single raindrop is nothing extraordinary within the context of an endless, eternal storm. Try, for a moment, to actually hold this image in your mind, not just intellectually accept it, but really try to picture it. Not one universe born from nothing. Not one bounce between two phases, but an endless, eternal, self-generating field, stretching without limit in every direction, continuously giving birth to universe after universe after universe, each one utterly isolated from the others by the very expansion that created them, each one convinced, if intelligent life happens to arise within it, that its own Big Bang was the beginning of everything that exists. It is a scale of existence so vast that our entire observable universe, 93 billion light-years across, containing perhaps 2 trillion galaxies, each with hundreds of billions of stars, would be reduced to something almost unspeakably small, a single bubble of foam, drifting for a moment in an infinite, eternally boiling sea. And even this staggering picture, vast as it is, does not represent the final word from theoretical physics on what might lie before, beneath, or beyond our own beginning. Because there is a fourth possibility, arising from an entirely different direction of research, one that doesn't ask us to imagine an ocean of energy at all, but instead asks us to reconsider the very number of dimensions that exist, and to picture our own reality not as a self-contained universe, but as something closer to a sheet of paper, floating in a vastness we cannot see. For decades, physicists have pursued a framework known as string theory, an attempt to unify all the fundamental forces of nature, including gravity, into a single, elegant description. At the heart of string theory lies a strange but mathematically compelling proposition, that the fundamental building blocks of reality are not point-like particles, as the standard model of physics describes them, but instead unimaginably tiny, vibrating strands of energy, or strings, and that the particular way each string vibrates determines which particle it appears to us as, whether it manifests as an electron, a photon, a quark. Different notes, played on the same fundamental instrument, producing all the diversity of matter and to remain mathematically consistent. However, they require far more than the 3 dimensions of space and 1 dimension of time that we experience in everyday life. Depending on the specific version of the theory, they call for as many as 10, or in an extended framework known as M-theory, 11 dimensions total. This might sound, at first, like a purely mathematical convenience, a trick invented simply to make the equations balance. But physicists working within this framework take the implications seriously, and one of the most striking implications concerns objects called brands, short for membranes, extended, multidimensional surfaces that can exist within this higher dimensional space, sometimes called the bulk. It is natural to ask, at this point, why we don't simply notice these extra dimensions in ordinary life, why the room around you doesn't obviously have 7 more directions you could walk in. String theorists generally offer one of 2 explanations. The first proposes that these additional dimensions are curled up impossibly small, compactified into tiny geometric shapes at every single point in space, far too small for any instrument we possess, or are ever likely to build, to detect directly, the way a garden hose looks like a simple one-dimensional line from a great distance, but reveals a second, circular dimension wrapped around its surface the moment you get close enough to see its true thickness. The second explanation, the one most relevant to our question, proposes instead that we are simply stuck to a lower dimensional surface within a larger space, unable to perceive the dimensions beyond it, not because they are too small, but because we have no way of leaving the surface we are bound to. Here is where the picture becomes genuinely staggering. In this framework, our entire universe, everything we can see, everything we can measure, every star, every galaxy, the 3 dimensions of space we move through and the 1 dimension of time we experience flowing forward, may all be confined to the surface of one such brain. Picture an enormously vast, 3-dimensional membrane, floating within a higher dimensional space we cannot perceive or access, the way a 2-dimensional sheet of paper might float within the 3-dimensional room around it. Every particle of matter we are made of, every force we can measure, other than gravity, is thought in this model to be trapped on that membrane, unable to leave it, unable to travel into the higher dimensional bulk that surrounds it. We are, in the most literal sense this theory can express, confined to the surface of our own reality, like ink permanently bound to a single page, with no ability to look up and see the desk it rests upon. And if one such brain can exist, floating in this vast unseen bulk, there is no obvious reason why there could only be one. String theorists working on this framework, including researchers such as Paul Steinhardt and Neil Turok, developed a specific model, sometimes called the ekparodic scenario, in which multiple brands drift through this higher dimensional space, sometimes separated by immense distances, sometimes for immense stretches of what we might loosely call time within the bulk itself. And because gravity, alone among the fundamental forces, is thought to be capable of leaking out of a brain and into the surrounding bulk, distant brands are proposed to be able to feel each other's gravitational pull, slowly, almost imperceptibly at first, drawing closer together across the emptiness that separates them, page by page, drifting toward one another. Over what might be an almost incomprehensible span of time, this attraction could pull 2 such brands into a slow, inexorable approach, closing the distance between them, until finally, they meet. And when 2 of these vast, membrane-like universes collide, the energy released is described, in this model, as being catastrophic and total, an amount of kinetic energy so extreme that it converts, in an instant, into a violent eruption of heat, particles, and radiation across the entire surface of both brands simultaneously. From the perspective of any observer confined within one of those brands, unaware of the higher dimensional collision that just occurred, this event would appear as nothing less than the sudden, explosive birth of an entire universe, hot, dense, expanding outward in every direction. In other words, mechanical, almost reassuringly physical, about this version of events, compared to the others. A collapsing universe reaching a quantum floor and rebounding still asks us to trust equations describing a regime no instrument has ever probed. An eternally inflating field of pure energy asks us to accept a substrate outside of anything resembling ordinary space or time at all. But 2 enormous sheets, drifting through a higher space, drawn together by gravity, and colliding with tremendous kinetic force, is a story built from ingredients we already understand intimately: attraction, momentum, impact, heat. It simply plays out 1 dimension removed from anything we can see, like a shadow cast onto our wall by a struggle happening in a room we can never enter. Under this model, the question what happened before the Big Bang has a startling and almost tangible answer. Before the collision, there were 2 separate, quiet, cold, nearly empty brands, drifting slowly toward one another through a higher dimensional space, for a length of time that might have vastly exceeded the entire 13.8 billion year age of our own universe. And what we experience as the beginning of time is, in this framework, simply the local moment of impact between 2 vastly larger structures, an echo of a collision happening 1 dimension up from anything we are able to directly perceive. It is worth pausing here to be honest about where we stand with all of this. The Big Bounce, eternal inflation, and the multiverse, and colliding brands in a higher dimensional bulk are not competing final answers, each waiting to be crowned the single truth. They are serious, mathematically rigorous research programs, each grown from genuine cracks in our understanding of extreme physics, each still very much under active investigation, debate, and refinement by working physicists. Some of these ideas make predictions that are, at least in principle, testable, subtle signatures that might be imprinted on the pattern of the earliest light in the universe, patterns that future instruments may or may not detect. Others remain, for now, almost purely theoretical, elegant but unconfirmed. None of them has been proven. None of them has been fully settled. What they share, remarkably, is that each one takes the same starting wall, the singularity where classical physics breaks down, and rather than treating it as an impenetrable end, treats it as a signpost pointing toward a deeper layer of reality still waiting to be understood. This leads, finally, to the reason none of these pictures can simply be checked by looking and seeing which one is correct, and why the matter remains, for now, a frontier of theory rather than a matter of direct observation. The honest answer lies in a wall of light that surrounds us in every direction we look, a wall we can never see past, no matter how powerful our telescopes become. It is called the cosmic microwave background, the faint, ancient afterglow of the early universe, and it exists because for the first roughly 380,000 years after the Big Bang, the universe was filled with a hot, dense fog of charged particles, so thick that light itself could not travel freely through it. Photons were scattered, absorbed, and re-emitted constantly, trapped, the way light is trapped and scattered inside a thick cloud, unable to travel in a straight line for any meaningful distance. It was only once the universe had expanded and cooled enough for electrons to combine with nuclei and form stable, neutral atoms that this fog finally cleared, and light was set free to travel unimpeded across the cosmos for the first time. That very light, stretched and cooled by billions of years of cosmic expansion, is what we detect today as the cosmic microwave background, and it represents an absolute, physical boundary on what we can ever directly observe with light of any kind. We cannot see further back than that moment. The fog itself is opaque. It is not a matter of needing a better telescope. It is a fundamental limit built into the nature of light and matter. When faced with a wall like this, to feel a kind of quiet frustration, the sense that we have been shown a locked door and told, politely, that we will never be handed the key. But that framing misses something important about how all of historical science has actually worked. We have never once directly witnessed the interior of a star, and yet we know, with remarkable precision, what is happening inside the sun at this very moment, because we learn to read the light it sends us. We have never once directly observed an atom with our own eyes, and yet we have mapped its structure so precisely that we can build machines from that knowledge, machines that now sit in your pocket. Indirect evidence, carefully gathered and rigorously tested, is not a lesser form of knowing. It is, in fact, almost the entire history of how human beings have ever come to understand anything beyond the reach of their own hands. Everything we understand about the Big Bang itself, the singularity, the bounce, the inflating field, the colliding brands, is therefore not something anyone has ever directly witnessed. It is something reconstructed, with extraordinary care and rigor, from the faint traces those events would have left behind, the way a detective, arriving at the scene of a fire that burned out millions of years ago, cannot watch the flames themselves, but can study the pattern of the ash, the direction the smoke stains lean, the fragments of scorched material left scattered across the ground, and from those clues alone, build a careful, evidence-based reconstruction of exactly how the fire started, how it spread, and what stood in that place before it burned. This is precisely the position cosmologists find themselves in. They study the cosmic microwave background the way that detective studies the ash, mapping tiny variations in its temperature, tracing the abundance of the lightest elements forged in the universe's first minutes, tracking the large-scale arrangement of galaxies across billions of light years, all of it serving as physical evidence, scorch marks left behind by a fire whose first spark we will likely never witness directly. And perhaps, when you step back far enough, that is not a failure of science, but something closer to its most humbling and most beautiful feature. We are matter that has organized itself, through billions of years of cosmic evolution, stellar fusion, planetary formation, and the relentless creativity of biological evolution, into a form capable of asking where it came from, capable of building instruments that can read the faint afterglow of its own birth, capable of constructing, from pure mathematics and painstaking observation, entire coherent pictures of events that occurred before there was any eye to see them, any mind to record them, any language in which to describe them. Consider, too, what it means that these four possibilities exist at all, not as idle fantasy, but as the honest output of careful minds following mathematics wherever it insists on leading them. A dying universe, coiling back into life. An endless ocean, forever giving birth to new worlds out of its own restless energy. Two silent structures, drifting for ages through a space we cannot perceive, before meeting in a collision that becomes, from the inside, a creation story. None of these ideas were invented to comfort us. None of them were built to satisfy an ancient longing for meaning. They emerged because physicists refused to stop asking questions the moment the equations grew uncomfortable, and pushed forward anyway, into territory where intuition offers no guidance at all, armed with nothing but logic, evidence, and an unwillingness to accept we simply cannot know as a final answer before every avenue had been exhausted. We may never know, with total certainty, whether our universe rebounded from the death of another, whether it condensed like a single drop of dew out of an eternal, boiling field of energy stretching without end in every direction, or whether it was born from the silent, colossal collision of two vast membranes drifting through a dimension we will never be able to touch. What we do know, what the evidence makes almost undeniable, is that 13.8 billion years of relentless, patient transformation took whatever came before us, whatever answer eventually turns out to be true, and shaped it, atom by atom, star by star, into something that can stand beneath the night sky, look upward, and ask the question at all. That, regardless of which wall we are standing against, and regardless of what ultimately lies beyond it, may be the most extraordinary consequence of the Big Bang that we will ever actually be able to prove.